All right, guys. So this is now chapter 17, which is energy in thermal processes and the first law of thermodynamics. All right, so in this chapter, we're going to continue our study of thermodynamics. So we're going to get some more fundamental concepts, including the first law of thermodynamics. So you can see, right? So thermodynamics and mechanics were considered to be separate branches until about 1850. And I mentioned that in class that um, about this time, up until about this time, scientists used to think that when energy or when the object basically um, is in physical contact with another object and they have different temperatures, then the reason that, let's say, then they eventually reach the same final temperature is because there is this substance they called caloric flows from one object to another. So this invisible substance goes from one object to another, and that substance then let's say makes the colder object increase temperature and warmer object decrease temperature. And that's what happens, right? When you put two things together and they have different temperature, usually the hotter object cools down and the cooler object warms up. And this substance that they call caloric, right? They basically they couldn't really experimentally determine because it was, again, sort of like abstract idea, theoretical idea, um, until we have them James Joule, who pretty much discovered actually what happens when you have two objects put together with different temperature. So he basically correctly showed that what happens here is actually the energy goes from one object to another. There's a transfer of energy when you um, put two objects together with different temperature, not some kind of substance that was lost from one object to another, but actually just the energy. So pure energy goes from one substance to another, and that's what let's say goes into changing the temperature. So he called this energy a heat, or the energy transfer. Heat is the energy transfer, and heat then is another way of transferring energy into your system. You can think of it like that, right? So if you have, for example, here's object one, and this is temperature of one, then here's object two, and this is temperature of two, and put like initial like that. Then if those temperatures are not the same, then there's going to be transfer of energy. And that transfer of energy, it was what we call heat. Heat itself is the amount of energy that has been transferred from one to another. Usually it goes from whatever the hotter object to whatever there's a colder object. So let's say T2 is greater than T1 initial, then this energy, right, the energy will flow from, hot to cold. Okay, so let's say this is then the direction of the transfer of energy. And the heat is then the amount of energy that has been transferred. Okay, so again, what the Joule did, James Joule, he showed that energy is the reason, or the transfer of energy is the reason that object changes temperature. And he showed that by showing that equal amount of change in temperature can be achieved by two ways: either um, adding energy in terms of heat, or doing mechanical work. So that's why he showed that heat is equals to the work, right? And or he showed like what we call mechanical equivalent of heat, and that experiment proved and verified that you can achieve the same increase in temperature if you do mechanical work on a system instead of just basically adding heat. And heat only can be added if let's say my system, for example, my system is object one, is in contact with another object that has a different temperature. Only then energy transfers as a form of heat. Okay, so but you can do a mechanical work on that. So maybe let's say take that and move it back and forth on a rough surface. So if you start moving back and forth on a rough surface, and some of the kinetic energy can be converted into heat energy, and then the object one can again warm up and increases temperature. All right. So then what we're going to do here, we can say, right, the law of conservation of energy emerges as a universal law of nature. He showed that, the energy is not in terms of object, let's say moving. So there's a motion energy, there's a height energy, there's a shape energy. Now there's also energy that basically goes into changing the temperature of the object. It's much more universal than previously was thought. All right. So then internal energy is then all the energy of a system that is associated with the microscopic components. Okay, so this is something we already talked about before as well when we covered the, like, let's say, friction. So the friction, remember, when some kind of object sliding on a rough surface, then in a way what we have here is the bottom of the surface of the object, let's say it's a box, right, then interacts with the molecules at the top of the surface of the ground. So that microscopic, at the molecular level, right, basically there's this force between them, this attractive force, and when you're pushing something, you basically have to also overcome that attractive force between those molecules. All right, so those molecules and atoms, right, basically um, responsible for this type of friction. That means you have to break that molecular bond between them, and some of that energy will go then into heating up the surface. So the kinetic energy due to its motion through space is not included, and internal energy is an example of, let's say, what we call, again, so internal energy does include kinetic energies due to not translational motion, but the random translational motion. That means, not going through space, but random translational motion of the molecules, rotational motion of the molecules, and the vibrational motion. So that means, um, the molecules inside the system, right? They can have this. Let's say if you have a container with some gas or something, like, let's say, or liquid, the molecules inside, right, then can have some kind of random translational motion or rotational motion if you give them a size, right? They can also have a vibration, especially in a solids. All right. So internal energy also includes intermolecular potential energy. All right. That means one of the things we're going to study again in this chapter is the heat. Again, heat is the amount of energy transferred, and internal energy. Some books also use thermal energy instead of internal energy, but they're basically same thing in this case. So work done on or by a system is a measure of the amount of energy transferred between the system and its surroundings. And the heat is the amount of energy, Q, we use Q for that, transferred between a system and its surroundings due to the temperature difference. That means what we given here is two different mechanisms. One is the work done. The other one is basically heat, or the transferred heat, which is the amount of energy transferred. That means this is two ways you can change the energy of the system. That means this is two mechanisms of transferring energy. So then we have W for the work done, which we have studied before, right? So then this work done is equals to the integral of F dot dl, right? Which is basically the dot product between force and displacement. And, going, let's say, from, let's say, L1 to L2, some points 1 and 2. And then now we have Q, which is then, not the work done, but, basically this is the heat, which is due to the, change in temperature. That means this is only if the object or the system is in contact with another one that has a, different temperature. So that means, basically there's a, you know, temperature dependent. So depend on temperature difference, like this. So we have those two mechanisms, and right now we're gonna then spend some time learning and studying this concept of heat, because more or less the concept of work we know already, but we don't know how to apply work concept to the ideal gas law, for example. So we're gonna look at this concept of heat. We're going to look at in terms of what are the requirements or what are the applications of heat, and then we're going to combine that together with the work done, and we're going to look at in terms of this internal energy. And then we're going to study basically the how the internal energy of the system can change due to those two different mechanisms of transfer of energy. All right, so let's look at again that remember the caloric substance that I mentioned. Well, it's still around, it's still being used, even though now we know that there's no such thing as some kind of substance that flows from one object to another. That's just energy. But use even this calorie as ends up staying as a unit. So historically, you can say that calorie was the unit used for heat. 1 calorie is the heat necessary to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. The calorie used for food is actually 1 kilocalorie. That means it's still used in US for the, uh, let's say, for the food energy, right? Amount of food energy in the, let's say, in the groceries and things like that for anything you buy. So whenever you see like 100 calories, 200 calories, or the daily, maximum of, 2000 calories, those are, in terms of amount of energy, food energy you should, you should be gaining, right, when you eat things. But that the thing is, let's say if you're given, let's say 2000 calories, that's actually given as capital C, and not necessarily lowercase. And there's a difference. 1 calorie like that is 1000 small calories. That means this is, in terms of the way things written here, like more of like, let's say, and this is nothing but, I would say, a nifty, PR scheme to make something much larger appear to be something a little bit, less, let's say, frightening. For example, when you look at the daily intake, so it's 2000, you know, calories, which doesn't seem that bad. But in reality, that's where each calorie is 1000 actual calories. So this is 2000 and three more zeros, right? So this becomes now 2 million calories. That means, when you're buying a chocolate bar, for example, which is 140 calories, in reality, this is 140 and with three more zeros, right? So now it's 140,000 calories. So it looks much scarier, right, than 140 calories that you're willing to, let's say, take. So this is something like, to make some values appear to be a little bit less, let's say, frightening. I think that's that's the only way I can kind of like explain this, because what we have here is, the food information is in calories, but it's in actually kilocalories rather than calories, but very few people actually aware of that fact. Anyways, so 1 calorie, small calorie, actual calorie, is 4.186 joules. So this is what we call mechanical equivalent of heat, and this is one of the things that also was discovered by the James Joule, right, when he did an experiment. So this is conversion from old units to a more of a new units, which is in terms of joules for the energy. So again, SI units for the heat is joules, and sometimes you might be given things in calories. Still, let's say in chemistry, I think they use calories sometimes, and some, for example, when I teach physics for health science majors, it's everything just over there in calories. So, but in this class, everything should be in joules. Whenever there's in calories, we need to then convert to joules anyways. All right. Now, in terms of for us to calculate amount of energy that goes into heating this, let's say the substance to a certain, temperature, we need to then, as I said, right, we need to transfer energy. For example, if you have a container with some liquid, in it, right? So let's say there's some liquid. So M represents the mass of the liquid. Let's say the mass of the liquid, and then Q is then the amount of energy that needs to be transferred. So let's say, I don't know, let's say for example, 10 kilogram of water then increases temperature from, let's say, initially 20 degrees Celsius to, let's say, final of 40 degrees Celsius. Let's say 20 degrees Celsius increase. Okay. So we want to take 10 kilogram of water and, increase its temperature by 20 degrees. Now, what we do here is, as I said, right? So this heat works when you take your system, in this case, this 10 kilogram of water, and put it in contact with another source that is hotter, because we want to increase the temperature. In order to increase temperature, we have to add energy. So let's say we put it on some kind of hot plate. So some kind of hot plate then will be much hotter than our system. Then the energy then will flow into our system. Okay, energy going to flow into our system, and the energy then is Q, is proportional to the amount of mass that we have, amount of substance we have. So more water I have, more energy needs to be transferred, right, in order to change the temperature from 20 to 40. It also depends on how much change I want to achieve. Let's say now, like let's say that is proportional to delta T. So then Q, again, it's in joules, so the amount of energy needs to be transferred is proportional to mass and proportional to delta T. Then whenever you go from proportionality sign to equal sign, you introduce a constant, and that constant is this guy over here, which we call specific heat. So the C here is the specific heat, and the specific heat is amount of energy per unit mass required to change the temperature of a substance by, certain degrees Celsius. Okay, and if energy Q transfers to a sample of a substance of mass m and temperature changes by delta T, then you can, find the specific heat using this ratio. So then this specific heat is experimentally determined volume. So let's say then you can transfer known amount of energy into a substance, see by how much the temperature changes, how much mass you have, and then you can calculate the specific heat, for example, for water, for aluminum, for mercury, for hydrogen, and so on and so forth. But what we can see here is then the specific heat is a constant quantity for a substance. So let's say if it's water, specific heat of water is exactly the same for regardless of, let's say, what experiment you do, because again, it is a proportionality constant. So that's why the specific heat is essentially a measure of how intensive a substance is to the addition of energy. So that means substances that have a small specific heat can heat up, or change the temperature very, quickly and by a lot when little of energy is added. Substance with a large specific heat then more resistive to the changing, or the transfer of energy and change their temperature only by a little bit. So that's kind of one of the things we have. So mass here has to be in kilograms. So then delta T has to be in then, degrees Celsius or Kelvin, because it's a delta T, can be either way. And then the specific heat is then joules per Kelvin, or the joules per kilogram, sorry, degrees Celsius. Okay, because joules is the unit that has to be surviving, so it has to then cancel, let's say, uh, kilogram and Celsius. So then you calculate the amount of energy. So for example, specific heat for water is then exactly that, 4186 that we looked at, that number, right? So, but in terms of if you're talking about, let's say, kilogram, is then 4,186 joules. So let's say if I have 10 kilogram of water, then this is specific heat of water, which is then 4186 joules, and then times, let's say, 40 degrees Celsius minus 20 degrees Celsius, which was my delta T, right? And I can then calculate the amount of energy then, transferred, which is 10 times 40, 4186. So it's roughly, so it's 41,000 and times another 20. So I don't know, like, let's say roughly 84,000 or something like that. So about 84,000, maybe a little bit less, but roughly 84,000 joules. So that's the amount of energy needs to be transferred to increase the 10 kilogram water from 20 degrees Celsius to about 40 degrees Celsius. All right. So there's a table that you guys can find in the textbook, and that gives you the values of the specific heat. And the specific heat, again, is different depending on the substance. Okay, so I don't believe I have this, the table in my lecture notes, but there's in the textbook, or you can just pretty much Google it. Let's say find it online. But whenever there's a problem on the quiz or on the exam or a recitation, you either will be given the specific heat, or let's say you will be asked to calculate specific heat. That's another thing that we're going to be able to do. But the idea here is this. So you take the mass in kilogram times the specific heat of a substance, then times the temperature difference or temperature change, right? And again, temperature change can be either in Celsius or Kelvin, because delta T in Kelvin is same as delta T in Celsius. All right. Now, if the temperature increases, which means that the delta T here is a positive quantity, which then give you Q, which is also positive quantity, because mass is always positive quantity and specific heat always a positive quantity. That means the Q being positive or negative completely depends on the delta T. And Q and delta T, if are positive, then energy transfers into the system. Okay. And which means then the temperature increases. Okay. So if the temperature decreases, means then delta T is negative, which means then the Q is negative, right? Because if delta T is negative, Q, which is an MC times delta T, well, if this is negative, then Q is also negative. In this case, means that energy transfers out of the system and the temperature overall decreases. All right. So when you look at the table of the specific heats, one of the things you will see here is that water has by far the highest specific heat. And the reason, let's say, for most of the commonly used substances, right? The reason because what we have here is water is resistive to the let's say amount of energy added. That means when you add energy into this into the system, where do you have water, right? So the temperature changes, but not by a lot. So that's actually a very good thing, because for example, our oceans, right? So during the day they're under the sunlight, and they absorb a lot of energy from the sunlight, because the environment is hotter than the let's say oceans. So then energy is absorbed, right? It goes into from let's say air right into the water. And during the nights when there is no sun right outside, the air is much, or the environment is much cooler than the water, so the water basically releases right energy. So that's why, let's say, during the day the water is a little bit warmer, during the night it's a little bit cooler, but it's not like big difference. So let's say during the day the water in the ocean is not boiling because it's absorbing all that energy, right? Because if it has a small specific heat, all that amount of energy that added to the water, right, or is absorbed, it will start boiling, right, because of that a lot of amount of energy it's added. And during the night when it releases all that energy, it will start then freezing, which is a good thing, right? We don't have that when during the day oceans boil and during the night ocean freezes. That's because it has a very large specific heat. All right, so one of the things we're going to then be doing here is in the next several slides, then we're going to be learning on how to let's say calculate this amount of energy, and what are the conditions that to take object from, let's say, from one temperature to another, and what are the things that, let's say, requires for us to do. Okay, so there's a number of ways that we can approach this, but let's talk about this one interesting technique that we can use. So it's a technique to measure specific heat of some kind of unknown substance. Okay, so and this generally involves, let's say you take a container, and let's say it's a closed container, and you have a let's say a liquid water, for example, and the mass of the water, that specific heat of the water, and then you have the initial temperature of the water, because you have, let's say, a thermometer inside, and we can measure the specific heat of the water. Sorry, the temperature, initial temperature of the water. And then you take some kind of substance. You don't know so what type of substance it is, but you can just find the mass of the substance and put S for the substance. So you put the mass of the substance, put it on a scale and find the mass. But we don't know what type of substance it is. So one thing we can do, we can put this on a hot plate, and we can increase its temperature. So let's say then we measure its temperature using thermometer. So this is initial temperature of a substance. And let's say, for example, it's I don't know, 100 degrees Celsius. And let's say water initially at 20 degrees Celsius at the room temperature. And then what we do here is we take this substance and put it inside water. Okay, put it inside water. Now, one of the things we have here is this. Because this is closed, an isolated system, and you have only two substances, right? Water and this unknown substance, two objects, right? Then what we can have here is then, because they're in a different temperature, right? So initial temperature of substance 100, initial temperature of water is 20 degrees. So there's going to be a transfer of energy, and energy always will go from hotter into colder. So then one of the things we can remember from a previous chapter is that two things with different temperatures put in contact, they're going to reach what we call thermal equilibrium, right? That means eventually the temperature of the water final will be same as temperature of this unknown substance final. Okay, so they will have a final temperature. Okay, so then this will allow us to find out how much energy was gained or lost, because one of the things we have here is this. So because they're going to reach exactly same final temperature, amount of energy that was gained by water is exactly same as amount of energy was lost by the unknown substance. So what I can say is that so Q water is mass of water specific of water, then times delta T. Then Q for the substance is mass of the substance times specific of the substance times delta T. And because it was an isolated system and you had put them both in contact together in an isolated system, then the net amount of heat energy transfer, which will be Q water plus Q substance, will be zero, because water will be gaining energy. So it's going to be positive because its temperature will be increasing, and the substance is going to be losing energy because its delta T going to be negative, because it goes from higher to some, maybe let's say, I don't know, let's say 42 degrees Celsius, some kind of final temperature. So that means one thing we have here is then Q water is then minus Q substance equals zero, or Q water is equals to Q substance. That means they're going to have exactly same, amount transferred, right? So that means what we can do here is, this is, by the way, this is known as a calorimetry, and this is calorimeter is basically a device in which the energy transfer takes place. So we can isolate it and have, let's say, the Q cold equals to the negative Q hot, means that same amount of energy, but one is gaining, the other one is losing. Okay. So then one thing we can say is that, for example, mass of water times specific of water times delta T then equals to negative mass of the substance, right, times specific of substance times delta T. Okay. So, and then if I divide both sides by mass of the substance and delta T, which are known quantities, then, and then, the negative move it there, because this delta T is going to be negative. So the negative going to cancel out. So then you can calculate the specific of the substance, which is then how to find the specific of the substance. And once you calculate that, then you can find out what type of substance it is. Is it aluminum? Is it tin? Is it, a brass, or whatever it is? So you can calculate that from this. All right. So again, this is a technique that we can use to find the specific heat. So this is another way of finding specific heat of unknown substances. Again, that's why specific heat is experimentally determined quantity. All right, so this is basically, I know what I just talked about in terms of the finding the specific heat. Just basically calculate this Cx quantity. All right, so now one of the things we're going to do here is this. Let's say I have my substance here is water, and what I have here is I have water initially as an ice cube at initial temperature of, let's say, negative 15 degrees Celsius, because at negative 15 degrees Celsius, water is ice. But I want this to go all the way to the final temperature of, let's say, 115 degrees Celsius. Okay. The question is how much energy do I need to transfer so that I go from negative 15 to 115? So now I know this is water, right? So, and let's say this is a 5 kilogram, ice cube. Well, then one thing we already learned here is this, and the Q, which is the amount of energy, equals mass times specific this times delta T. So then, one thing you can, assume that we can, let's say, use this equation where this is 5 kilogram times specific of water, which is 4186, then times, 115 minus negative 15 degrees Celsius, and we calculate the amount of energy. So let's say whatever we get over that. So should this give then the amount of energy that we need to take the ice cube at negative 15 to the final temperature of 115? Well, the answer is no. We cannot do that, and that's simply because there are phase changes happening. As if you take the water from negative 15 to all the way 115, because there is a temperature between them, or two temperatures, that will require a change of phase. So one, remember, occurs when you go from solid to liquid, so it's a melting or freezing point. The other one is when it goes from liquid to gas, which is boiling. So the solid liquid occurs at 0 degrees Celsius, liquid to gas is 100 degrees Celsius. And obviously both of those are within this range. That means by the time we go from negative 15 to 115, we're actually going to have to go through two phase changes. So that's why that equation itself is just not enough. You cannot just use that equation to calculate the amount of energy it takes to increase temperature from -15 to 115. Okay, because when there is a change of phase, that means solid to liquid or liquid to solid or solid liquid to gas and things like that. During that process, when the something is melting or freezing or evaporating, right, energy transferred into the system does not change the temperature. It goes into changing the phase. That means one of the things we're going to do here, then we're going to see that there are two equations. There are two equations for this type of processes. So one equation that we already learned, which is then mass times specific heat, then times, let's say, not necessarily the water, right? Times delta T. So this is energy that goes into changing temperature. So changing temperature while the object is same phase. Okay, while the object is in the same phase. But when object changes phase, then there's a different equation that we have to look at. So because the energy depends on, another quantity, right? It doesn't, again, the energy doesn't go into changing temperature, it goes into changing the phase. All right. So then this is known as a latent heat. So then the latent heat for a phase change, which is L, quantity L, is equals to Q over delta M. That means this Q is the amount of energy that goes into changing the phase divided by, the mass, changing mass. The reason we have delta M, because sometimes this, you might add energy, but this energy will go into only, let's say, changing half of the, substances, uh, phase only half of the substance. So let's say if you need 100 joules to convert all your substance from a solid to liquid, but you add only 50 joules, then it goes only changing the half of the substance into water, right, into liquid, but other half then still stays solid. All right. So that means what we have here, this equation then goes into, calculating the amount of energy that requires to change phase. And there's actually, like, let's say, plus minus involved, which is kind of like, hidden plus minus, because plus indicates that you're adding energy, minus indicates that you're removing energy. And plus minus is not needed for the previous equation for the Q, for the change in temperature, because delta T already takes care of that. But here, delta M is always still, basically going to be positive, right? The idea here is then this is just the mass, and this is latent heat, which is always a positive quantity. So then you have to manually add positive, negative, in front in order to represent energy added with, compared to energy removed. All right. So then latent heat has two types. One is a heat of fusion. So we write it as LF. What it is used during the melting or freezing. So basically this is at 0 degrees Celsius. The latent heat of vaporization, LV, is used when the phase changes boiling or condensing. So this one then 100 degrees Celsius. That means each one has a very specific, let's say, volume. LF and LV are not the same. They have like different values. And then we can then just basically calculate, using this specific LF, LF and LV and LF, right, for a specific substance. So for example, water has a different, like let's say hydrogen is different, and so on and so forth. Okay. Again, the positive sign is used when the energy is transferred into the system, which will result into melting or boiling. The negative sign is when energy is removed, which results freezing and condensing. Okay. So things like this. So to understand that, we're gonna, the role of latent heat in the phase changes, we're gonna take 1 kilogram cube of ice, basically kind of somewhere I was kind of going over, right? So let's take then, let's say 1 gram cube of ice at negative 30 degrees Celsius, then take it to all the way to a steam of 100 degrees Celsius. And in the process, I'm going to show you, let's say there's a diagram that we can use, which, helps quite a lot when we're doing this type of calculations. All right. So again, we start with mass of ice, which is 1 gram, and the temperature initial of ice is then negative 30 degrees Celsius. And we want to then take this all the way to the final temperature, well, we can see, right, I'm not writing ice anymore because final temperature of 120 degrees Celsius, this is basically going to be steam rather than ice. All right. That means we're going to be, starting with ice and go all the way to the steam. That means we have to have two phase changes, and we also have to melt and then boil, which means then we have to add energy into the system. All right. So we start by doing a chart like this, where the y-axis is the temperature, and then the x-axis is basically amount of energy added as a function of time, pretty much. All right. So first we take ice at negative 30 degrees Celsius. Okay. Then, so this is basically where the ice is right now at negative 30 degrees Celsius, and this is the 0 degrees Celsius. The graph represents how at this first stage you have to add energy using this equation, Q equals mc delta T, where now we have mass of the ice, specific of the ice times delta T, where we take the mass times specific of ice, which is 2090 joules per kilogram degree Celsius. That means this is something, to put it down somewhere. So it's 2090 joules per kilogram degree Celsius. This is specific of ice. Then times the temperature difference, which is, 0 minus negative 30, so it gives you 30 degrees Celsius. Because this is the temperature change for ice. Because ice can only go up to 0 degrees Celsius. Okay, so this is basically, let's call it stage A. So for the stage A, you take the ice at negative 30 degrees Celsius and you increase the temperature by adding energy all the way to 0 degrees Celsius. It cannot go beyond that. So, and you calculate this to be 62.7 joules. That means 62.7 joules takes 1 gram of ice at negative 30 to 1 gram of ice at 0 degree. Now it has a now we have a 1 gram of ice at 0 degrees. Then we continue adding energy. Okay, so if we continue add energy, that means we go to the stage B. For stage B, then any energy added will not go increasing temperature because ice already at its maximum temperature. So then energy goes into melting the ice. Okay, that means we have to use the, heat of transformation equation. So which is LF, which is heat of fusion for water, which is 333 or 3.33 times 10 to the 5 joules per kilogram, 10 times the mass of our ice cube, which is 1 gram. So we get 333 joules. That's the amount of heat needed to completely melt the ice. Now we got this, we were right here. So now we have a 0 degrees Celsius, but we have water now, 1 gram of water. That means if I add energy, now I can increase temperature again. But this time we're dealing with water. Okay. So, but you can see, right, for this process, state B, we have then ice plus water because we are melting the ice into water. For stage C, then we go into adding energy to change the temperature of water from 0 degrees Celsius to 100 degrees Celsius, because that's the maximum we can take the water. Again, it's a mass of the water, which is same as for the ice, times specific of the water, which is 4.19 times 10 to the 3, which is basically 4.186, just rounded, joules per kilogram degrees Celsius, times the temperature change, which is 100 minus 0, so 100 degrees Celsius. So we calculate 419 joules. That means this stage C is the amount of energy added to water to take it from 0 to 100 degrees Celsius. Because at this point, now we have a water at 100 degrees Celsius, and there is nothing we can do about increasing temperature of that anymore. So then we go to stage D. Stage D is when we have to then boil all that water into steam. And you can see, right, it takes the longest time and most energy. So, because this is again another transformation equation. Q equals LV times delta M. In this case, LV is the heat of vaporization. For water, then this is 2.26 times 10 to the 6 joules per kilogram. So you can see, right, the difference here is that, this is basically 2 million joules for each kilogram of water, which is, quite a lot compared to everything we had before in terms of heat of fusion or the specific heat. So, and then this is basically the times the mass. And then what we get here is we get 2000 2200, let's say roughly, joules, compared to, for example, only 63 over here, or about 400 over here, and about what is it, like about a little over 400 over there, right? So much greater amount of energy required to boil this. But here then we're sitting at at this point with 100 degree Celsius, but we have done now all steam, or you can say like all gas, right? So then this is basically, we're done with stage D. We go to stage E, where then we add energy to take the now we have 1 gram of gas, right? One gram of steam, from 100 degrees Celsius to 100 you know uh, 120 degrees Celsius. So that's why it's 120 minus 100 gives us 20 degrees Celsius difference. So this is the mass, same mass, and this is then specific of steam. So it's 2.01 times 10 to the 3 joules. So which is roughly about 2000. So 2000 2010. So generally it's 2010 joules per kilogram degrees Celsius. That's for the specificity of steam. Okay. So that's the speed of steam, and then we get another 40 joules. All right. Now, what is then the total amount of energy? Well, total amount of energy is everything added together. So everything added together will sum up to 3,110 joules. Okay. So that's the amount of energy needed to take, and you have to see, right? You have to say that is QA plus QB plus QC plus QD plus QE, sorry, this is equal to then my Q net. Okay, that means there is a those two stages. There's a change in temperature of already ice, water, and liquid, and then we also have two phase changes during that. That's why I cannot just use one equation to take it from negative 15 to all the way to, or negative 30 to all the way to 120, because there's a transformation happens between those two temperatures. All right, so let's take an example here. Let's do an example. So Carlos takes 10 kilogram bag of ice at negative 10 degrees Celsius from the freezer and puts it in the back of his truck. Unfortunately, he forgets about it and the ice melts. How much heat energy did it take to melt the ice completely? All right, so we take the mass to be 10 kilograms, and so mass of ice, and then the initial temperature is then negative 10 degrees Celsius. It's completely melted, but we just basically stop when it completely melts. That means the final temperature is technically still zero. So then by looking back in terms of those stages, right? So if I look at back a stage, what I have here is that I have a stage when it changes temperature from negative 10 to zero, another stage when it's basically melts. That means here I have just two stages, right? It's QA plus QB, where QA is then M ice C ice times delta T, taking it from negative 10 to zero. Then another one to melt, so mass of ice times LF. Okay, so those are the only two stages I have. All right, so then this is 10 kilograms times specific heat of ice, which is 2090 joules per kilogram degrees Celsius, then times temperature change, which is sorry, 0 minus 10, then plus 10 kilograms times then heat of fusion, which is 3.33 times 10 to the 5 joules per kilogram. Adding all this together, we get 3.5 megajoules, which is million joules. And that's because we have, 10 kilograms compared to, let's say, 1 gram in a previous example. So the amount of energy needed is quite a lot. All right, so here's another example. So 30 grams of copper pellets are removed from a 30 degrees Celsius oven and immediately dropped into 100 milliliters of water at 20 degrees Celsius in an insulated cup. What will the new water temperature be? All right. So what we're given here is basically example of calorimetry, right? So you have some kind of substance like a copper, and then after that, at least we now know what type of substance it is. It's a copper. We know the specificity of copper and everything, and then we have water. So let's do this. So mass of the copper, and put like C for copper, is equals to 0.03 kilograms. Okay. Then initial temperature of copper is 300 degrees Celsius. Then mass of the water given in terms of 100 milliliter. Okay, so then we have to convert this into the, let's say, kilogram, because in a way what we're given here is, um, sorry guys, this is not the mass, this is actually the volume of water, right? So 100 milliliter. So then we have to convert this, or find the mass from this using this equation where mass equals density times volume. Okay, remember density of water is 1000 kilogram per cubic meters. Okay, so then mass of water will be equals to density, which is 1000 kilogram per cubic meter, then times the volume, which is 100 milliliter, converted to basically cubic meters, where 1 milliliter is 10 to the negative 6 cubic meters. The mass of water is 0.10 kilogram, which is like 100 grams. All right. So then, using this, we can calculate the final temperature, because think like this. So let's say here's my system with water, and then we put like a copper inside, and as we learned, right, so then Q water plus Q copper going to be equals to 0. Okay, which means then we're going to have to have a same amount of energy, transferred between them, right? Because think like this. So let's say how much energy I have transferred to water is exactly the same energy that was transferred out of the copper. So that means that's why the sum is basically 0. All right. So from here, what I do is this. So mass of water times specific of water times T final minus T initial. This is for water. Because final temperature of water is exactly the same as final temperature uh, of the copper, because they're going to reach thermal equilibrium. So then this is plus mass of water, mass of the copper, specific of copper, times T final minus T initial copper. Okay, so then this is equals to 0. So if I rearrange everything, so I'm going to get mass of the copper, specific of copper, times 300 degrees Celsius. By the way, that basically rearranging means that you distribute everything, right? So basically mass of water, specific of water times T final minus mass of water, specific of water, T initial, right? And then rearrange, factor out T final, and then, get this final equation. So mass of uh, water, specific of water, 20 degrees Celsius, which is its initial temperature. And then this is divided by mass of copper, specific of copper, plus mass of water, specific of water. Okay, so then, all right, everything is given, right? So here's the mass of copper. Um, this is the mass of water. Specific of copper is equals to uh, 385 joules per kilogram degrees Celsius. And obviously we know specific of water as 41, let's say 90, you can write. So let's say joules per kilogram degrees Celsius. All right, so if I plug in everything, all those values, right, I'm going to get 28 degree Celsius as a final, temperature. All right, here's one more example. So the engineer wishes to determine the specific of a new metal alloy. A 0.15 kilogram sample of the alloy is heated to 540 degrees Celsius. It is then quickly placed in a 0.4 kilogram of water at 10 degrees Celsius, which is contained in a 0.2 kilogram aluminum calorimeter cup. The final temperature of the system is 30.5 degrees Celsius. Calculate the specific of the alloy. Now, for this, what we're saying is that the cup is also part of the system. Generally, this calorimeter is a cup that is specifically designed to isolate the system from environment. So if I have a water inside, then I can say that when I'm looking at in terms of the calorimeter cup, right, and then let's say the water, they're sitting together at the same temperature. So let's say mass of the CAL, which is calorimeter, so mass of the cal is equals to, so we're given 0.2 kilograms, 0.2 kilograms. Mass of the water is then 0.4 kilograms. Okay, And then the mass of the A for the alloy is then 0.15 kilograms. All right. So the initial temperature of water, or the calorimeter, right, cal, is 10 degrees Celsius. Initial temperature of water is also 10 degrees Celsius. And then initial temperature of the uh, alloy is 540 degrees Celsius. Then final temperature for all of them equals to one another, and that's 30.5 degrees Celsius. Okay, so then they all reach the same final temperature because they, you put the alloy inside, they all reach the same final, equilibrium, right? Thermal equilibrium. It means then we have Q alloy plus Q water plus Q calorimeter is equals to 0. Okay, which is mass of alloy times specific of alloy times delta T. So which I'm going to write it like this. So it's final, which is 30.5 minus initial, which is 540. Then plus mass of water, specific of water, that times then final 30.5 minus initial, which is 10. Then plus mass of um, cal, then specific of the calorie, right? And this is aluminum calorimeter, which means that we know then the specific heat, let me put it like this, for water is 4190 joules per kilogram degrees Celsius. Specific heat of, for example, then calorimeter, which is aluminum, right? So it's given as 900 joules per kilogram degrees Celsius. That means I have, the mass of the calorimeter, the specific heat, then also the temperature, which is 30.5 minus 10 degrees Celsius. And this is equals to 0. That means all we have to do here is move everything to the other side, like this, right? And then eventually divide by mass of the alloy times temperature change, 30.5 minus 540. And then just solve for the specific heat of the alloy. Okay. Just plugging in the mass values and everything, we can calculate specific heat of the alloy to be 497 joules per kilogram degrees Celsius. And we compare it to see what type of, alloy this is, right, in a book. And then if you can find a match, it's good. If not, then maybe we invented new alloy. All right. But that's kind of like how to find the specific of this unknown metal.